Alright, so let's say you're given this diagram here of a collision between two masses, and the question says, consider the collision above between a small ping pong ball and a large bowling ball. We should expect that after the collision, the ping pong ball should travel backwards with approximately the same speed as its initial velocity, since it is much lighter. Use collision theory to prove this to be true. To start, let's assume this is an elastic collision, which means firstly that we can assume that the conservation of momentum holds, which means that the momentum before is equal to momentum after. And also for an elastic collision, the kinetic energy is conserved, which means the total kinetic energy before is equal to the total kinetic energy after. So we can apply this to our example. Note, we need to show why the velocity after for A is going to be equal to the negative of the initial velocity of A. We can start with the conservation of momentum equation. Knowing that it is a two mass system, there's the ping pong ball and the bowling ball. We can denote them as mass A and mass B. And so the total momentum is going to be equal to the momentum of A plus the momentum of B. If we use this, we can convert the equation to look like this. And then we can apply the definition of momentum equal to mass times velocity. So the momentums of A and B can be written as so and apply to the equation to give this. This is going to be the momentum equation for the motion. And then we can look at the kinetic energy equation because the kinetic energy is also conserved given by this equation here. That's a two mass system, so the total kinetic energy before is going to be equal to the kinetic energy of mass A plus kinetic energy of mass B, and the same for after. And then we can apply the definition of the kinetic energy, noting that the kinetic energy before for the mass B is going to be equal to 0 because the velocity of the bowling ball at the start is 0. And if we apply the kinetic energy definition, we get this, and then we can cancel out the 1/2, arriving at this equation here. So this is the kinetic energy equation for the system. And so we can solve for the velocity after for A and B in terms of the masses and the initial velocity of A. And this will help us explain why the velocity of A after is approximately equal to the negative of the initial velocity of A when the mass of A is much less than the mass of B. And to do this, we can first rearrange the momentum equation for the velocity of B after. And we do that by bringing this term to the other side. Since both these terms on the left have mass A, we can pull A out and we arrive at this expression here. And then we can also rearrange the kinetic energy equation for VB after by bringing this term to the left-hand side, also bringing out the mass A like so. We arrive at this equation here. And now what we can do is divide the second equation by the first equation. So this is the second equation here, and we can divide the left side by the left side of 1, and we can divide the right side by the right side of 1. And if we do that, we can do some simple cancellations. And then we can note that this expression here on the top can be rewritten in this form here. This is going to help us cancel out the denominator, because if we replace it, you can see that these two terms cancel, leaving us with this expression here. So this is the velocity relationship between mass A and mass B for an elastic collision. So we can plug this into our equation 1. So this is our equation 1 here, and then we can replace VB after. Then we can isolate for VA after, and if we do that, we get this. So this is the velocity of A after as a function of the masses and the initial velocity of A. So now we can look at if mass A is much smaller than mass B, what's going to happen is MA minus MB is going to be approximately equal to negative MB, and then MA plus MB is going to be approximately equal to MB. Since mass A is so much smaller, we can almost completely ignore it. So that means we can replace the top terms with negative MB and the bottom term with MB, and if we do that, we get this, and then that cancels out, giving us this final expression here. And this is why when the ping pong ball elastically collides with the bowling ball, the velocity of the ping pong ball after is approximately the same as before, because the mass of the ping pong ball is so much smaller.